The Isaac Newton telescope on the island of La Palma in the Canaries. Astronomers here are observing a very fascinating and enigmatic object, NGC 1275, a violent galaxy right at the center of the remote Perseus cluster of galaxies. In the oldest optical photographs, NGC 1275 looks like a giant elliptical galaxy with some structure near the top edge. But then spectra were taken. The Doppler shift gives the radial velocity in our line of sight direction, and in the region of that structure there are two distinct velocity systems. This is interpreted that we're looking at not one but two separate galaxies, a giant elliptical galaxy and a less massive spiral galaxy seen edge on. They're both moving away from us, but with different radial velocities. Radio observations made using the 21 centimeter line of hydrogen confirm this and show that the spiral galaxy is in front of the elliptical galaxy. The two galaxies are moving towards each other. The observations don't tell us how far apart they are. They could be very far apart, both within the Perseus cluster, but not related. But they could be very close together, about to collide. And there's another puzzle. When the galaxy is photographed in the light of a strong emission line, such as the red line of hydrogen, H alpha, we see a complex filamentary structure. What is the physical nature of these filaments? Indeed, are they flowing in or flowing out? These are questions that are not yet settled. At Jodrell Bank in Cheshire, radio astronomers have studied this object using the large dish in combination with smaller telescopes at remote sites, working together in pairs. This is Table, a satellite radio telescope that works together with the large dish. Signals from it are transmitted across by microwave radio link to Jodrell Bank, 11 kilometers away. A single radio telescope with a very large aperture gives good angular resolution. Two separate small telescopes linked together can mimic one small part of that large dish. As the Earth rotates during the course of a day, one appears to run round the other, and they trace out a ring. And if we can vary the separation between the two, given enough time, we can synthesize a single very large dish. And so the technique is called aperture synthesis. The signals from the two telescopes are combined electronically using interference techniques. So the system is called an interferometer. The widest separation used gives the finest structure in the source, and indeed radio astronomers have extended the baseline used to span the whole surface of the Earth, giving very high angular resolution. And this very long baseline interferometry, VLBI, reveals the structure of the compact source right at the heart of NGC 1275. The structure changes with time. There's an expansion. This is evidence for the ejection of matter from the central heart of the nucleus. There could be a black hole there, powering this massive ejection of matter into space. But what we're interested in is the structure and the scale of the filaments. To study that, we still need to use an array of telescopes, but with baselines that are of much smaller size. The telescope at Table is one of a number of telescopes based on Jodrell Bank that form an array called Merlin. This combines several different pairs of radio telescopes. They are unmanned outstations operated remotely from Jodrell Bank. The name Merlin stands for Multi-Element Radio-Linked Interferometer Network. Professor Rodney Davies is an Australian who has worked at Jodrell Bank for many years. He has been fascinated by NGC 1275 throughout his career, and he's recently been studying it using Merlin to learn more about its intricate nature. As we'll see, these radio observations turn out to be related to the filaments seen optically in H-alpha radiation. One of the unsolved problems about the filaments is, what is the source of the energy that they are radiating? To tackle this problem, optical observations are needed. By looking for the atomic spectral lines emitted from different places along individual filaments, astronomers will learn about the energy source and the motions there. Similar emission lines come from a region around the nucleus, but they're much stronger from there. This is a problem worthy of the Isaac Newton telescope on its splendid new site on La Palma. Of all the islands in the Canary archipelago, La Palma is ideally suited for astronomy. Well above these clouds, its skies are clear and clean and still, for many nights all the year round. The giant volcanic caldera rises up through the clouds, and few besides astronomers venture to its summit. We're going to follow the observing run from the time when the team begins assembling on the mountain. The visiting observer is Dr. Catherine Boisson, who comes from Meudon near Paris, who will be working in international collaboration with the observatory staff. Some months earlier, Catherine had applied for time on the telescope to study NGC 1275, and she has been allocated the next 4 nights at the observatory. At the base of the telescope is the detector to be used, a spectrograph containing a diffraction grating which spreads the light into the different colors of the spectrum. Unlike a star, a galaxy is an extended source, and it produces a series of spectra. Catherine has selected the particular grating she wants to use tonight. When it's placed with the spectrograph slit, it gives a line of spectra across the galaxy. The spectra are recorded using a sophisticated detector that counts every photon as it arrives. The next step is to set up the position angle of the slit across the galaxy by rotating the telescope baseplate to the correct position. For tonight's observing, the slit is being placed east-west across the nucleus. For tomorrow night, the plan is to place it along one of the filaments. With the slit in position, the detector is ready for the night's observing. The galaxy being observed is 100 megaparsecs, over 200 million light-years away. But even so, the telescope with its giant 100-inch mirror is large enough to gather the light from the very faint outer filaments of NGC 1275. Vincente Reyes, whose home is on La Palma, is the night assistant. He has the responsibility of looking after the operation of the telescope. The next job is to find the object. Under computer control, the telescope is moved to point towards its target.
we are there. That is it. Yeah, I think it's this one, no? Yeah, it's this one. See it? Yeah.
Two Galaxies.
Two Galaxies.
Yeah.
It's this one here, yeah.
And then you got the two.
The double one here. This one. So we'll go to the cast. There he is.
It is.
Okay, this one, no? Just in the slip.
Now they've found the galaxy, it will be tracked by locking onto a nearby guiding star.
Move to the guiding star here. Okay.
The telescope is ready to take the first spectrum.
So 50, 10, 10. And it's all?
Yeah. Then you should give a scale, something like 0.1. And you should define where you want to have it on the screen.
It's Catherine's first visit, and the observatory's resident astronomers help familiarize her with the complex equipment.
Yeah.
Okay.
An axis.
Axis, yeah.
Instead of an I.
The exposure is going to be in the green-blue region of the spectrum. This includes the hydrogen line H beta.
We're going on H beta, I think. Seems to
Okay.
be much better. But we have to move to the nucleus if we want to get something. Put the slit on this one.
Okay.
So,
Stop that and remove the telescope.
yeah.
A minute move of the telescope, and the slit is right across the nucleus, and so the exposure can start.
Open the shutter.
Come on. Okay. One.
Everything set? Well, there we go.
Okay, it's fine. This.
And should get a nice display of the spectrum.
Here are the beginnings of the spectrum, which will build up as the exposure continues. The beauty of this instrument is that the observers can sit back and watch this happen.
It's very nice.
Now, if everything works out nicely, we see single photons coming in as balls on the histogram, like raindrops. Well,
Here they
there they
come.
come. How much would that be? We get 10 photons in 50 seconds. That makes 1 photon per 5 seconds.
It's not too bad.
Goes very fast.
Yeah, we can recognize already O2, H beta and O3 light.
Shows you that the lines are much brighter than the sky. No, that's not true because we have subtracted some of the sky. So we got there H beta, oxygen 2, oxygen 3.
There is some H gamma.
Already they can begin to identify the emission lines.
Some neon 3, you think? Better
Sorry?
check. It seems that there is some neon 3 appearing here. But we perhaps better check with the sky. It's not a problem of sky subtraction. H gamma, H delta.
No, it's very nice.
Some
You see them
nitrogen
really,
1, 2.
you see them really coming in one by one.
Mm.
It's beautiful.
This is continuum also.
So far then, the continuum emission from the active nucleus is emerging, as well as several intense emission lines. As the night goes on, the lines can be confirmed.
What have we got all there? H beta,
Yeah, H beta.
oxygen 2.
From left to right, we've got oxygen 2, neon 3. Then H gamma, H delta, H beta, all what you want in H, O3. And it seems there's some nitrogen 1. longuard of...
Already there is enough to show that the night's observing is likely to be highly successful. Over the 4 nights of the observing run, the team recorded several very good quality spectra of the nucleus and of the filaments. It will take several months of painstaking effort by Catherine and her colleagues back home in Paris to analyze the spectra. But other observations have been made on this system. From an X-ray satellite called Einstein some years ago, it was found that there is a very strong, compact X-ray source centered right on the nucleus of this galaxy. As well as that, there is a very extended X-ray emission from the whole cluster. X-ray emission coming from a very hot, low-density gas that spreads through the space in between the galaxies. Indirect evidence for this gas comes from radio observations of another galaxy belonging to the Perseus cluster, NGC 1265. It's a head-tail radio source with a swept-back appearance that stretches 1 million light-years into space. This is produced as the galaxy, a conventional double radio source, moves through the intergalactic gas. Many people believe that these strange filaments of NGC 1275 are formed from this hot intergalactic gas, which as it cools down can be seen in optical radiation and is flowing in towards NGC 1275, the central galaxy in the cluster. But not everybody agrees with that. NGC 1275 is itself a very strong, compact radio source. Since the very early days of radio astronomy, Perseus A, as it's called, has been recognized as an important radio source in the sky. But with the development of the Merlin system, there came a new result about these filaments. So are they indeed flowing in? Rodney Davies.
The radio data shows us the very opposite. The central regions of NGC 1275 have a very strong radio source within them, and coming out of that there is a radio jet which we are convinced is powered from that central source and indicates that we have material flowing from the center.
As the Merlin network makes its observations, the signals come in from the different pairs of telescopes, and as they arrive, the raw data can be monitored. The map of the radio structure produced contains spurious aspects coming from the very strong, compact central source. This totally obscures the fainter outer structure that we're interested in. But part of the magic of the Merlin system is in the techniques that are used inside the computer to clean up the map and remove all these spurious signals from the strong central source. We then see what is left, and there's a jet. This jet is lined up almost exactly with one of the filaments seen in the outer optical structure. And this optical filament is exactly lined up with the small jet seen in the nucleus of the galaxy in the VLBI pictures. The radio jet found from Merlin and also this optical filament must be material that has been ejected from the central source. So here is evidence for an outflow in one of the filaments. So, are we faced with a controversy that some observations imply that the filaments are flowing in and others that they are flowing out? It seems that the simplest way to reconcile these observations is to recognize that there are 2 different kinds of filaments, with both a coming and a going of material. But observation of NGC 1275 using the sophisticated infrared telescope that the UK has erected on the summit of Mauna Kea in Hawaii has added to these speculations. Rodney Davis has found that, compared with what is seen for normal galaxies, there is very strong infrared radiation coming from the central parts of the galaxy NGC 1275. And the closer in that we observe, towards the center, the stronger is this excess of infrared radiation.
We interpret this as being star formation in the center of the galaxy. It is also possible that it might be synchrotron emission of the same nature as the radio, but we feel confident that star formation is a major component of the infrared emission. Also, we have other evidence that there is a supply of material for forming stars, and this is the infall of the spiral galaxy towards the elliptical galaxy. And this will bring in an abundant supply of gas which will enable an efficient star formation to take place.
On this model, as the two galaxies collide, material is pulled from the spiral galaxy and falls in towards the center of the elliptical. There it meets gas already there and collides with it. Shock fronts are formed, and these trigger off a burst of star formation. The new stars are seen through the infrared radiation that comes from their thick circumstellar dust shells. But what if these galaxies are very far apart and not colliding at all? Another source of the material to form stars could be the filaments. If they are falling in, they too could come in right to the central region of the galaxy and there form new stars. To decide between these models, we'll need new optical observations. And still other observations will be made that will take the story further. Someday we shall understand NGC 1275 and the countless other violent galaxies in the universe.